Hey, how's it going, everyone? Welcome, CNG128 students. This is Dr. Hisham Said. This video here, I'll introduce to you the economical evaluation of engineering alternatives. And in this, through first, what is a systematic approach to compare between engineering alternatives from the economics point of view? Which include two main steps here. Uh, the first one, or one of the major steps here, is to define the planning horizon, and then the next one is specifying the time value of money. And we'll see the different methods to do this economical evaluation and comparison between alternatives, which two of them we'll cover in this video, or the second part of that video, is present worth and future worth. So the process here includes 6 steps. The first here is defining your investment alternatives or engineering alternatives, which is a typical thing in the engineering design process. So you need to identify your alternatives, and they need to be feasible alternatives, mutually exclusive, and collectively exhaustive. So the first one is feasible, meaning you need to come up with a feasible design. That's straightforward. The next one is mutually exclusive, so there's no overlap between them, and together they represent the whole possible alternatives. So if there is one of the alternatives is a mix of two, then you need to mix these two and include that as a third or whatever additional number or additional alternative for you in the design or in the analysis. These are the conditions to define an alternative for a design or engineering problem. And we see here also it's either or, but not both. So you don't have overlap between them. And the last thing here, one of the possible alternatives that most people skip is do nothing. So you need to think about maybe that's a hard problem to solve, and just keep the status quo and don't propose any solution to it. So the next step would be to define the planning uh, horizon here. Planning horizon here, we see that we call it here useful lives. So you need to, for every design, you need to think about its useful life. So we see here equipment one can live up to 10 years, but the second one is only living to 15 years. Um, so there is an assumption here if you have that case. So to be able to compare apple to apple is you assume that alternatives can be renewed indefinitely. And we'll see how that can make our life easier in comparing fair between these different life alternatives. So the different ways here we can say the first method here is using the least common multiple of lives, which we will use. The second alternative here, the shortest life. The third one is the longest life. So from their names, you can get a sense of what they mean. But we'll introduce here the least common multiple of lives. When you have different alternatives with different lives, what you'll do is, for example, you have alternative A of 3 years and alternative B of 5 years. So the least common multiple is 15 years. So your planning horizon would be 15 years, where over these 15 years you will repeat alternative A for 5 times. So you will keep equipment, if it is an equipment, you keep it, buy a second one, a third one, fourth, fifth, and then you end up with the end of your planning horizon. While alternative B equipment, you buy it for one, throw it away, buy another one, a second one, and then a third one, and then you end up with the same planning horizon here. So that's the simple idea of this least between alternatives. So once you define your alternatives, defining the planning horizon, now you need to develop the cash flow diagram for each alternative. And in the class, I mean, to have a problem given to you, that's already done in the problem. But in real life, you have just an engineering solution. So use equipment A, or this is the design for a bridge. So you need to estimate um, and do a lot of assumptions, actually, not some, a lot of assumptions to come up with costs and expenses and maybe expected revenue. So there are different techniques here used: cost accounting, estimating, and life cycle costing. So we'll not cover that in the class. Actually, there are whole classes covering just the first one, uh, life cycle costing. So here in the course, problems are giving you already. The cash flows for them are set. So that step is just part of the process, but most of the problems given to you, except maybe for the group project that you work on. Um, the next step would be to specify your time value of money, which we discussed before in classes, that time value of money is actually a relative, subjective thing. It's different from a person to a person. And the difference here from a person per person, because every person secure the budget for a project uh, from different sources. So you're securing the capital here from either debt or equity, and debt here can come from loans and bonds. So maybe based on your credit history, you can get a better loan than me, and then that will affect your time value of money. Uh, Bonds as a similar process. So we'll cover these in the lectures, loans and bonds. Uh, the next source of capital is actually equity. So you can have stocks. So you release stocks to bring equity or money from investors, or you can reinvest your earnings and retain them. So we call return earnings. So these stocks, maybe your own stocks, so you have your own time of value of money, and then these are exterior time value of monies. And the idea is you combine both. And again, we'll not cover how you combine both. You can make the simplest way is making average of the different time value of money or the sources of securing the capital. We come up with a single uh, minimal attractive rate of return. So this minimum attractive rate of return is the one that you always, open your eyes very big for it, and make sure that any investment or any engineering alternative is paying back that minimum attractive rate of return. Or when you use that to calculate present worth, always present worth or future worth or annual worth is positive value. So time value of money, again, in problems, it's given to you. Or it's maybe given as an unknown and everything is given to you, which we call it here internal rate of return method. So we'll see that method in other lessons. Um, Done with that, you're almost ready now to compare between alternatives and select. So you're done all the steps prerequisite to be able to compare and select your winning alternative here. So how to do the comparison between alternatives here? There are um, different methods, and the whole idea is you need to get equivalent worth for every cash flow. So you're squeezing every cash flow into just a single value, and the single value should be similar for other cash flows. So for a cash flow, you will calculate the present worth at the present time, and then the other alternatives you do the same. So you're comparing present to present to present, and then you're comparing apple to apple. You can look at the future and then calculate the future worth for alternative A, B, C, and then you can compare between them. Annual worth, you can do the same, but now imagining that you're calculating the equivalence annual cost for every alternative. So it's on an annual basis you compare between alternatives. And a last thing here is the internal rate of return. It's a little advanced and has a lot of advantages over the other three methods, and we'll cover that in a lesson different than that. So in that lesson, we'll actually cover present worth and future worth. They are very straightforward. We'll see how we can apply them considering different lives, using the least common multiple life. So that will illustrate that um, using the exercise in a couple of minutes. So present worth here again, we did that in just in a single problem basis, and we can see here that the let's sit here. Okay, so you can see here the present worth. You're squeezing the whole cash flow into a present the value in a present time. And you can do that by discounting all future values and bringing them to the present. So you're comparing like to like, or apple to apple. And as long as I'm not telling you this investment is a one-shot investment, so we'll see that in another lesson. Then you assume always it's renewable uh, indefinitely, and then you compare based on the least common multiple method. Um, Approach to compare between alternatives is future worth. So it's almost exactly the same as the present worth, but you're just calculating the value equivalent to a cash flow, not in the present, but in the future. So that's the difference here, and it applies also the same rule here. That you always assume it's renewable unless the problem or the case here says it's not renewable. If it is renewable, then you use here the least common multiple to compare between alternatives with different lives. So, hey, how's it going? So welcome to the second part of that lecture. This lecture about the economic evaluation of engineering alternatives. And the first part we introduced the process. Now we are explaining it by solving that example problem. So we have here these two structures, Y and Z. Each one has its own cash flow characteristics. So we have here the first one, Y, is cheaper, but it lives shorter than the other one, and it costs more in maintenance. So now you cannot have a clear cut by looking simply at the numbers. You have to run life cycle or a whole cash flow analysis here. And the problem here asks for comparing between these two structures using the present worth and the future worth. Shown the cash flow for each one. And we see here structure Y is have a life of 12 years, and the expense here is 45, and then the maintenance cost here is 1,000. So that's need to be written here. So just write it. So you have oops. So that's the color. 1,000 per year. So that's the cash flow for Y. Cash flow for Z now spans for 24 years, starting from the end of the first year all the way to 24. Like I say, like my way of drawing the uniform series, like the nice decoration here. So I mean, just to show that it is a uniform series and you're recognizing it this way. So that will make your life easier when doing the cash flow calculations. So now to compare between these, as long as I'm not, or the problem doesn't say that you have to buy it one time and that's it. It's renewable. So based on the lives we have here, you can conclude that for 24 and 12, your least common multiple, it's clear that it's 24 years, which means that you will use Z for one time while Y will be repeated for a second time, so it will fit within the 24 years. So how is this repetition done? So we will, at the end of the 12th year, you will you're done with that structure and you're building a new one. So you're building it with the initial cost here of 4,500. So 4,500. And then you have these annual expenses of maintenance are repeated, and they are repeated uh, starting from year 13. And then starting from here, you have now you will realize the maintenance for the first year of the second equipment, which is year 13. Uh, and then that will be repeated over the next the remaining years here. So that's how it's repeated. You can see now the first cycle. Oops. 1 minute. We draw that again. So the second cycle here is similar to the first cycle, just like copying that one and pasting it here. So that's how the cash flows look like. And we figure out least common multiple 24, and now the next would be calculating the present worth. So what we'll do now is, which is part A for that problem. So part A present worth. So for present worth, you will calculate the present worth of the first cash flow. So present worth of Y. And the first thing here, you need to plan ahead. So one thing is think about how many terms you're calculating. So I have here, if you zoom in and cash flow Y. So some people would say I have 4 terms. I have 1. So the first investment of the first equipment, the second investment of the second cycle of that equipment, and then I have a uniform series here, and then a uniform series there. So some people would say I have 4 terms. But actually, these two series are actually almost continuous. They are continuous. Or actually, it is a continuous uniform series starting from year 1 to year 24. This break here is just artificial. You can simply uh, continue this as if as it's a uniform series and so on. So why? Because this arrow here represents the maintenance of the 12th year. This arrow here represents the maintenance of the 13th year. So they are continuous. It's just we while we're copying and pasting and say the cycles of that equipment, we skip that small link. But here in that case we have actually 3 terms. So 1, 2, and then 3. Okay, so that's planning ahead. I know now I have 3 terms to calculate. So knowing that, I have the 4,500, and I'm calculating the present worth, so it is at its own time. So what I will do is I will say present worth here will equal 4,500 multiplied by 1. And I would say this is negative because now it's expense. So this is the first one. The second term here is the 45 at year 12. So at year 12, I need to bring it to year 0. So what I will do is going back here to my equation. I would say now negative, so it's another expense, 45 multiplied by p given f factor. So you're having this as a future, and you're dealing with it as bringing it to the present. So that one will be p given f 5%. This is our interest rate or minimum attractive rate of return, 5%, and then 12. So done with two terms so far. So the last term is 1000. It's a uniform series from 1 to 24, so it's 24 years. And you're bringing it to its value to the present. And let's do now the term for that one. So here you'd say that would equal to, it's another expense, so minus 1000 multiplied by, I'm bringing this to the present, and it is a uniform series. %, and then I have it for actually 24 years. And that's the equation for present fourth y. It's just a matter now for bringing the values of these factors and plug it in the formula. So the first one is p given f 5% and 12. So to bring it from the table here, p given f, so this is the column, 5% is this whole page. So p given f, and then I'm looking for 12. So 0.55684. So that's the first factor. The second factor is p given a, so that's the column, and then same interest rate, but then 24 years. So that's the column here, p given a, and then 24. So I'm dealing with this value here. Nope, it's not clear. 1 minute. So that one, p given a 5% and 24 is 13. That one. Okay, so that's the factor for p given a. Another factor is p given f and 12%, which is this one. So 0.55684. So using these factors now, I'll write them on top of my formula here with a different color. So p given f 5% and 12 is 0.55684. And then the second factor, p given a for 24 years is 13.79864. So by grabbing these values, plug it into the formula, you end up here with your p given a or present worth of y to equal negative 20,000 804.4. So that's the present worth of y. The next would be present worth of z. So present worth of z let's plan ahead. So, present worth of C, I have actually three terms: initial investment, maintenance, and salvage. So, I have three terms to write, and let's see the factors for each. Present worth of the Z structure. So, that one would equal the initial investment of 10,000. So that one negative 10,000. And then the next would be the maintenance of 720. Multiplied by, this is a uniform series for 24 years for the same 5% interest. So that one will be, so P given A, 5%, and then 24 years. So that's the second part of our formula here. This last part is the salvage value of 1800. And for that one, it is actually a positive value. So that one is 18 plus 1800. Multiplied by, now this is a future, and I'm calculating its present. So that one is P given A, or actually P given F, 5%, and then 24. So that's the formula. And what we need to be getting now is the factors. So the factor that this one here, P given A 5% and 24, is the same as this one. So that's the factor we already have. And then the P given F 24, we did not get it before. We got only for the 12. So what we need to do is going back to the table. This is the P given F column. So going all the way down. And then I'm pointing here to the 24 years. So 24, that's the value we need to get. So plug it into the formula we have. And that factor here would be 0.3. That's a weird 3. Okay, 0.3. 1007. So that's these are the factors we have, and then once you do the calcs, you will find that your present worth of Z that one here is also negative. So negative 19 3 7 6 minute 6.89. So that's the answer here. And now while comparing, now we see both of them are negative. Uh, so which makes sense because if you look here in the table, nothing is given referring to revenue. So all of them are negative except for a tiny revenue at the end, the salvage for structure Z. So the idea now is both of them perform the same function, the same revenue, which we ignore, and then we compare between them and select the one that gives us the least cost. So picking the least cost by looking at both negative values here, you pick that structure Z because it's giving you the least cost. So that's only part A of the problem. But the good thing here, once you set up the problem by drawing the cash flow and breaking down the cash flow into the components, that every component refer to a term in the equation you have, that term would be just changing by changing a formula when you move from a present worth method to a future worth method. So we're almost done with the problem here. Just a matter of repeating almost the same formulas uh, under the future worth calculation. So stick around. I will just set up the problem for the future worth because now we already have the understanding of the problem, but just applying a different technique. So stick around. Okay, welcome back. So I saved you of the hassle of dealing with my tablet, drawing cash flows and uh, writing the equations for it because we did the present worth part A. So uh, that's actually part B, the future worth method. So here again, like we set already the problem and we know the components of every cash flow. So we have here one, two, three parts for the first cash flow for structure Y. So this one, 45, you bring it to the future by f given p 5% 24. That one, f given p, but now for 12 years only. And then this whole series from the beginning to the end, 24 years, you'll bring it to the future by f given a. So future worth f given p, f given a, f. So it's f given something. Uh, how to get the factors? Again, you were dealing here with f given p, 24 and 12, and f given a. So if you just check the table here, we're dealing with the first column, f given p, and this is for the 12 years, 24 years. And then the next factor is f given a. And then f given a, you have here, this is the factor for it. So again, it's a systematic process. Once you get used to the tables, it's just grabbing values, propagating the equation, and when you do the calculation, you end up with this value here. So that's the future worth of structure Y. And when we calculated the future worth of the present worth of structure Y, it was negative. So when you calculate the future worth of Y, you expect it to be also negative. The next would be for structure Z, we have 1, 2, 3 parts, 3 terms. So we have here again 3 terms. This one, the initial investment, you bring it to the future by f given p, the 24-year factor. We have here the 1800, the salvage value is exactly at the future point we calculating the future worth of the whole cash flow. So we just multiply by 1. And then the annual uniform series 720, you multiply by the future worth of that whole thing, the annual series for 24. And then you use now the same factors for the f given b 24 and the f given a 24. So you end up, when you calculate the future worth of z, again, you expect it to be negative because the present worth was negative. Then you have these two values, similar to the previous conclusion. We select the one with the least cost to us. So we select equipment Z or structure Z. I'm sorry. So that's the long way actually of calculating the future worth, because there is a short way that we can do, which is we already have the present worth. So we can use the present worth we already calculated to calculate the future worth. So once you have the present, you can calculate the future because it's the same two cash flows we're dealing with. So I will show you here how to do that, but you need to understand the risk. Is if present worth is incorrect, the future worth will be incorrect. So just consider this risk when you do it this way. Uh, so what I will do now is show you another way, and another solution here is mainly using that formula here. So the future worth equals the present worth multiplied by the factor. So the factor we have here is the F given P 5%. And now we're moving from the present to the whole future of the whole cash flow. So from 0 to 24. So that's our formula here. So I want you to try it. So use the present worth we calculated previously, multiply by the F given P factor for 24, which you already have here, and give it a try and see if you will end up with the same future worths using the present worths we calculated before. So that concludes this example here. Again, we use the present worth, future worth, and it's a renewable investment. So you need to get the least common multiple, replicate the investments or alternatives that are less than least common multiple. So here we repeated the Y structure into 2 cycles or 2 lives, and then the Z is already 24, so it's only one cycle. Calculate, then break down the cash flow into the terms or the components that you will refer to in the equation, and you should be fine. You'll do awesome. So please practice that problem by yourself, shut down the computer and do it yourself. And of course, feel free to email me and contact me for any questions. All right. Thank you so much for listening.